Exercise 1.6. All strings of the form WW where W is some string. This one's a particularly tough one, and it happens to be the case that's not context-free. I'm not going to go through the full detail, but I'm going to give you the rough sketch. So we do our usual thing. So, there exists some n such that for all z in the language, for z sufficiently large, pumping lemma applies. Where's my pumping lemma? It's over here. We'll keep it handy. Okay, so what string should we choose such that when we pump things up, it's going to fail? So I'm going to pick the string n zeros and ones, n zeros again, and ones again. It's pretty clear this thing is in the language, because if we let alpha be this, if alpha is 0 to the n, 1 to the n, then the string is clearly alpha twice over, right? So this thing's definitely in the language, and it's definitely at least as long as n, because its length is 4n, which is bigger than n. So then there exists some decomposition such that pumping lemma holds, so we have to show for every decomposition it fails. So we write z as uvwxy. And where can vwx live? Well, if we sort of draw out what this string looks like, so a bunch of zeros, and a bunch of ones, a bunch of zeros, a bunch of ones. There's basically going to be a handful of distinct cases. So the middle part could be inside one of these 4 blocks, like strictly inside, so it's just all made of the same character. Or it could straddle one of these 3 boundaries. So it could sort of be overlapping the zeros and ones here, it could overlap the ones and the zeros here, or it could overlap the zeros and the ones here. Basically, for whatever the decomposition this is, VWX has to be one of those combinations. So I'll do the proof for it lies inside a block, and I'll do the proof for the first boundary, and I'll leave the rest to you as an exercise. It's basically the same thing again. So we'll do cases. VWX is in the first block of zeros. First block of zeros. Which means it lies somewhere here. So that means VWX is going to be some number of zeros. U is going to be however many zeros left over, which I guess is n take I many zeros. And Y is going to be the whole rest of the string. So, I've lied a bit. This is going to have to be worse than that, actually. It's going to be n take I take j, and then y is going to be j zeros, because VWX could take some in the middle, and then u is here, and then y is everything else. So u is how many zeros left over when you take away the middle and y, and then y is going to be some number of zeros, and then all the ones, and then all the zeros, and then all the ones again. And it's pretty clear because Vx is not empty, and VWX is made entirely of zeros, that Vx is going to be made entirely of zeros, right? So if we choose M to be 0, UWY is in the language, and what's UWY going to look like? Well, it's going to look like the whole string with some zeros out of this first block knocked out. So UWY, it's going to be 0 to the k, 1 to the n, 0 to the n, 1 to the n, where k is strictly less than n, because you have to delete at least 1 0. Okay, so could this thing be written as alpha alpha for some alpha? We're going to show no, so let's see why. So I'm going to argue the only possible place we could split this string is down the middle. So suppose we split it somewhere else. Suppose we split it to a little bit left of the middle, like here. Then the string is this alpha will start with a 0, and this alpha will start with a 1, and that's no good, right? And if I split it slightly to the right of the middle, then the first alpha ends in a 0, and the second alpha ends in a 1, and that's no good either, right? And clearly if we stray even further, I mean the strings are just not going to be the same length, right? So the only sensible way to split this is right down the middle, so the string alpha starts and ends with the same character. Sorry, both alphas start and end with the same character, so they have to because they're the same alpha. So that means alpha equals 0 to the k, 1 to the n, which equals 0 to the n, 1 to the n, which means these two exponents here have to match, so therefore k equals n, which is a contradiction, okay? So whatever decomposition we choose, it can't be somewhere inside a block of zeros at the start. And you could repeat this argument to show it can't be inside any of these blocks, because you basically cook up the same argument. You delete some bits, you show that the only way to break it up is in the middle, and you get a contradiction. So if it's not inside a block, that means it's got to be sort of lying over a boundary. So let's have a look at that case. So I'll do case VWX is over first boundary, which basically means it's lying somewhere here. Okay, so that means VWX is going to be some number of zeros and some number of ones. And either of these could possibly or can't possibly be empty, because otherwise we're back in this case here, right? If there were no zeros and it were entirely ones, that's basically the same argument here. So we're going to assume I is bigger than 0 and j is bigger than 0. So what does this leave us? U has to be some number of zeros left over. I'll pick a different letter, k. And then y has to be the rest of the string, right? So it's going to be some number of ones, 1 to the L, and then all these zeros here, which is n many, and then all these ones here, which is n many. Okay, and then we do the same trick as we did before. We just delete the v and the x. So choose m is equal to 0. So that way u, w, y is in the language. And what does u, w, y look like? Well, it's going to look like the same as the original string, but somewhere here we've deleted a bit, right? Which means this whole string here is going to have at least 1 0 less in this block than this block, or at least 1 fewer 1 in this block than this block. So, and we already argued before, the only way to split this string up is to have this first part as alpha and this second part as the second alpha, right? So regardless of what v and x are, we're going to obtain a contradiction because we deleted a symbol here or we deleted a symbol here. If you want the full version of this, the full version of this proof is in example 7.21 in the book, so I encourage you to have a look. But the idea here is I'm just trying to show, get the intuition for the proof. The proofs for the other boundaries are basically the same as this case here. You show that you delete a bit here somewhere, and then you unbalance the number of zeros or ones on both sides. That's how you're going to prove that.